Hello, this is Richard Collins with the Internet Foundation. I'm visiting NOAA, National Oceanographic and Atmospheric Administration, and there's a section called Rapid Refresh. I don't have an easy and accessible map of NOAA, its organizational and geographic network, how it works and what it works on. So let me what I was looking for were some 3D gridded forecast, so I can visualize easily a 3D volume of the atmosphere going up rather high, maybe 100 levels going up, and then some region, a relatively small pixel number, you say 100 by 100, so 100 by 100 by 100 is a billion cells, a billion voxels. And what I had read in here, and I can't find it again, unless you have a perfect memory, which I used to have, when I wasn't so tired, I would just memorize everything, and then I wouldn't have to look it up again. Now, how do you find it again? It becomes a problem. So where's the list of all the fields? Where's the list of all of the things? They're not in easy form. If it were me, I would have them laid out. Where are the locations? Where are the people? Where are the organizations? What money is spent on each thing? How long have they been running? An inventory, a picture, a model of the NOAA. The Department of Commerce has some things, but much of what NOAA does really doesn't belong in Department of Commerce, except in a very, very general sense. And there are all the NOAA dependencies, so all of the monies that they send out to research groups, other federal agencies, international agencies, other countries, maybe, I don't know. I haven't checked the financial records as well. So, gridded. Now, I'm down in the middle here. I actually got to HRRR. Now, let me go back a step. So let's go back to the home page here. So high resolution refresh, rapid refresh, assimilation, verification, innovation. That sounds really good. Assimilation, I guess, means gathering the data. Verification means making sure it matches. And particularly, it sort of implies that there's measurements and data and some models in there, some framework, a place to put everything, and some way to check whether it's correct or not. I'm just rambling here, trying to get myself oriented. Wrap plots. I don't want to look at. I just wrote him a note and said, I don't want to see pretty pictures because I can't do anything with them. Well, let's look at them anyhow. So here plots. What do they say? What are these? Okay, so that's kind of whatever. Let's see. Okay, so all right. So can I go back a day? The third. Let's go back to a full day. Oops. These are in small time steps, so let's go back just randomly in here. So these are full domain. Okay, now it resets. So now the table's filled in for, oh, not quite. Let's see. Are these days? Okay, 10, 11, 12. So this is going from there, full domain, 2nd August. Let's go back to, how far back can we go? Let's go back to the 21st, 10 Zulu. Here's 0 Zulu on the 22nd. See if that, yeah, okay, well, that's, okay, what's going on? So this says 1, 2, 3, 11 days. Is that what's going on? Okay, so experiment, wrap model fields experimental. That's what I'm reading up here. date 22nd July. Okay, so there. Let's see what else. Okay, so there's that's where I saw 12 kilometers somewhere, and all. So me, I would maybe because I need a context, a permanent context for everything. If I'm seeing it for the first time, I don't want to have to memorize, build a framework for myself, then implement that in terms of reminder. So I'm in. Is this a 13-kilometer world right here? Is that what we're doing? How many levels? How many things? What's the framework for this? Okay, so all right. So reflectivity. I just spent the last 5 days looking at the U.S. national radar, weather radar system. So I have a pretty good sense. Surface cape. Well, here's the case. That should be hoverable, right? Okay. Go to Wikipedia, look at any of the highlighted topics that are considered important enough to have their own page, and I'm sure Surface Cape, whatever that means, should have its own page. Let's try it and just see. Surface Cape. Okay, convective available potential energy. Very useful, very handy. I understand it completely. I just didn't know what the blankety blank acronym or abbreviation. Okay, so, but if you hover it, or let's see, there must be, you could hover it and actually have a list. You could have Wikipedia as an option, and then you could hover that. If you went into Wikipedia hover, you could hover any of the things inside of it. You could go down at least 3 levels there if NOAA would implement hovers. What are you doing? Previewing what's out there that people could go look at, but don't force them to go there and then come back. The difference is 100-fold in some cases. Okay? If the page you go to is a huge thing and has not the little bit of information you need, then it could take time. Surface cape. So weather.gov. Well, here's the thing. NOAA has been throwing a bunch of stuff over to weather.gov, and weather.gov is doing a lot of stuff and not really asking NOAA anything about it. I think that's what my impression of what's going on. Okay, so the surface cape, instant weather maps. Okay, so I'm not going to go there, but pardon me a moment. Okay, I didn't want my air conditioner to interrupt you. Okay, so there are surface CINs, which aren't explained either, so what do I have to do? I have to open a whole new page. Search that. Weather, NOAA, hourly mesoscale. See, mixed. Oh, did I get the wrong one? Yeah, it says mixed cape. Okay, that's wrong. Mixed cape. Or did I thought I just surface cape, mixed cape. All right, let me. I'd like to know these things. I'd like them to be immediately available. I have most all of this in my background. I've been studying physics for more than 50 years now, and I go into great depth on everything that I do. This bothers me because they've thrown them out and said, well, here's some standard levels that you're familiar with from the past. But me, I'm looking for 3D stuff, and I said, just give me the whole thing. That one of the dimensions will be the height. That's fine, or the pressure height, whatever you. Okay, well, So this has a lot of legacy views and visualizations tied to it. Uh, just for the heck of it. This is one day. And it's a picture. Now, immediately what I do, I'm glancing around, it says, where can I download this? I want that as numbers. I don't want it. Now let's see what we got. Composite reflectivity, surface cape. Oh, joules per kilogram. Fine, wonderful. Now I'm oriented. Why didn't they put joules per kilogram here? Where, you could easily put the units and dimensions right there. You could actually you could put in the name, or you could simply hover each one of them. I would prefer to, if I'm doing a first view of things, just give me a full table, just widen that, stick in the units and dimensions. How big is this doggone thing? Okay, when I'm hovering that thing, tell me how many actual numbers are involved, and then also tell me the size of it. If you're storing it, and it takes you, 1,000 bytes per field, that's a lot different than, if it's something more compact. All right, so composite reflectivity that I can connect to, presumably I can connect, either this derives from the radars directly, or it could be. So if I could go in and predict what the reflectivity is going to be, and then check it. That's what I would like to do. Or look at the radar and satellite and GPS and electromagnetic sensors, gravitational sensors, all of the different sensors, and say what's in each voxel, and then how's it going to look to each sensor. So basically, if you have 20 sensor networks, which is not, because there are many more than that, but taking a nominal 20 sensor networks, all looking at the same region of the end time, then each sensor will receive something from that area. And actually, if you do time of flight, if you measure on a fine enough time frame, short enough observation period, then you can determine where things are. Okay, just from the time. I did that years ago, and I've only recently come back to it, because you can go and say, well, okay, this thing is reading at a gigasample per second, and therefore I have about a meter resolution on the radial distances from each sensor. I do my simple correlations, and then I can probably come up with what data is available from a specific voxel. You can address voxels just simply by specifying the time delays and keeping them fixed, and then monitoring. So anyway, okay, so what do we got here? Surface cape, joules per kilogram, fine. Let me think about this for a minute. Joules per kilogram, now this is cool, okay. The gravitational field of the Earth, the gravitational potential itself, is in joules per kilogram. It's those are the units for potential. If I see joules per kilogram, I say potential. And it turns out, almost always, in all the different cases I've been looking at, the potential terms are additive, okay, and non-colliding somewhat. Okay, I'm not going to go into that right now. So the surface cape and surface sin. No, these numbers here. I guess, okay, 5,000 joules per kilogram. Okay, so let me think for a minute. 5,000 joules per kilogram. Let's see, these are 5,000 divided by 96,485 equals, I think I did that right, 0.05, that's twice KT. Okay, so that's there. So that's pretty coarse grain from we're looking at very fine details. Now these are the steps in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like 11 steps in here. So that drop that back. So it's about a fifth of KT is the resolution. Okay. So all right, let's see if hopefully I did all that right. All right. So that looks cute. Surface CIN. More capes. More unstable capes. So people like that potential unit. It's a great thing. The gravitational potential for all practical purposes, from when you're looking at the gravity networks, acts like a fluid. Okay, so it acts as though the gravity at a place is mixed up with the magnetic potential. You know, the also in joules per kilogram, where you have to make an assessment of the density of the material you're working with. And generally, it's just say air. Okay, I'm keeping it simple right now. I'm just looking at air, a little bit of water, and slowly working under the earth. Okay. So, but for air, you just work it out. Use the density of air as that. Do the magnetic properties per kilogram. Do your joules per kilogram for the phenomena you're monitoring, and everything's at the speed of light. Okay, so the speed of light and gravity. Okay, 10-meter wind, and I presume this means at 10 meters above the surface, the geopotential surface. So these are the flows induced by a number of things. Now the wind is square root of, okay, so the wind is, density, 1/2 rho v squared is equal to pressure in there. Okay, and the pressure, okay, anyway, so I'm trying to do this in my head. I'd rather have my little notepad and toolkit here and then refer to it in here. I'd like to look at the equations and the stuff right here. Just, I brought up this analysis. I don't know who did it. Like, I can't track down the authors of this. I don't know where this was done. I don't have reference to any of the software that's being used. I don't know what any of the data is for this. So I'm here looking at it and trusting. And it's mostly pretty pictures. Now, I've visualized all my life, so I can probably go in and guess about some of the things they're doing. But I don't want to move around visual pictures. What I want to do is to go and move the data, So this is what it looks like to be about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That's odd. 17. Okay, so you have that many levels, and I presume they put some slop in here. So the occasional down to smaller in there, and they didn't use a logarithmic to scope in and zoom in on the very small, nor also logarithmic to go in and zoom in and look at the high parts of this. So okay, so 20, they're smaller than 5. They're okay. 1/2 rho v squared. Okay, so these are meters per second. Holy crud! Pardon my French. I don't know. It says 10-meter winds, so hopefully it's all in metric. So let's see if I can do this. Okay. Okay, so this is 20 to 25, so 22.5, I guess the midpoint, x squared divided by 2 equals times 1.225, 310 Pascal. Okay, so that's going to be a pressure in Pascal. And divided by 1.01325, 3 thousandths of an atmosphere. So 3 parts per thousand variation in the local pressure from that. Okay. All right. I'm just getting myself oriented. I would rather have these other notes in there because I can do stuff, I can connect things if I have absolute units. If I have a pretty picture, it's a huge burden on me to do anything quantitative with a picture. I have done it when absolutely, let's check. Save image as PNG. Well, that's useful. At least it came out in hopefully a lossless format. Let's see, show it in the folder. Sorry, it came up on my other screen here. And properties. Okay, they didn't put in date taken. 32 bits. Well, that's interesting. I doubt it. I think what that is well, I have no idea okay, that's RGBA. So that's not actually 32 bits of data. That's probably encoded. Yeah, so it's not a real image. Okay. And so it's 712 by 696. Okay. But it's not. That's what. Anyway, sorry. I try to check everything. I try to think of everything in here as I'm trying to get these together. The satellites can see this. You got a station on the ground talking to the GPS. Any of the cell phones out there, they can monitor both frequencies now and look at the electron content along the path to the satellite. Eventually, the people are working on that pretty actively, and we're going to get pinpoint connections from all kinds of places, hundreds of millions of places potentially, from that surface up to the associated satellites. If the satellites are on the horizon, you're slicing through the atmosphere in many places. Now, where does the information needed? Well, you have a large city, a large number of cell phones, you get more points. You should be able to do that. All right, so gust, wind speed, same thing. So wind speeds, well, that's interesting. That looks like about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 32, 48, maybe about 40, 50, some of things. Well, that's a very striking color scheme. I'm sure someone has great aesthetics, but I would rather have the numbers. Okay. And you put it in Fahrenheit. Oh my gosh. Go sit in a corner. Okay. Do it. It has to be, if it's on the internet, it is supposed to be in an international standard, global standard. And right now that means metric, that means the SI system, and that means at least Celsius. I would prefer it just being Kelvin. But if you don't do that, then you ought to provide for every person who comes, let them set their own. So if you have a number like a temperature, you offer it in every temperature range. So if they want to have Fahrenheit for the temperature and they want meters per second for the velocity, and whatever combination they want, they should be able to pick that. So this is I use Okay. I won't say shameful too many times. Okay. SFC, surface temperature, maybe surface at 2 meters. Uh, I'd like to be able to do the difference here. Okay, if this is at one height and that's at another, what's the increment? Okay, I can, what, you're going to make me do that in my head? Okay, sorry. Those are really odd color schemes. There's no gradation. I think it's completely arbitrary. Does any of that mean anything? Is this color here? It's coming from is that color there from here, or is it from there? That's really hard to tell. If you're just that one, I don't know. Is it this, or is it one of these? Now you might be able to distinguish those, but I can't. I think that's wrong. Wrong in a moral sense. Wrong in a communication sense. Wrong in a collaborative sense. Wrong in a global human race I don't say race, I say global human species that needs to have things easier to learn, easier to work with. Okay. So what's this one? Potential temperature. Okay, that's fine. Presumably they converted their joules per kilogram into Kelvin. So the Boltzmann's constant, couple of standard things. You get 300 Kelvin. Now, I'm not going. I was going to talk about Stefan-Boltzmann relation, and that the temperature is actually a flux, which is T to the fourth, and I'm trying to sort that one out. Okay, 2 meter temperature, skin temperature. I don't know. Dew point. Where's your dew point explanation thing here? No one. Me. I have a decent memory still, and I just really, really don't want to have to memorize and remember the dew point tables. Okay. I don't have time to go look for them. If you search for dew point right now on the internet, if I just go out, there is no authoritative place on the internet for it. There are 100 authoritative places. There's 1,000 places, 10,000 places say we know what the dew point is, and almost none of them do it properly. You can't get it from Wikipedia. You can't get it from NASA. You can't get it from NOAA. You can't get it from NIST easily. And if you do find it, none of those groups work together. Okay, everybody just puts their own stuff on the internet. No rules or rhyme or reason to any of it. What's good for us is what drives every individual group. So, all right. So these are the issues I'm having to face every day, trying to look at the whole of the internet, its purpose, its structure, its future, its current methods and problems. All right, dew point temperature. Okay. Relative humidity. This could be done a lot better. That's really, if you're going to do it, just do everything to the same level of accuracy. Now, I know relative humidity is not done that well, okay, in terms of the measurements, the sparsity of the instruments. Now, LiDAR and radar and satellites could probably put some bounds on that. And I've seen some, columnar, soundings, electromagnetic soundings that do a pretty good job of at least tying it down. You dot the I's, cross the T's, fill in the blanks, you do the best you can. And then at least it's possible, if you have the basic equations, if you know the calibrations, you know the standards and the pieces of it, you know what instruments were used, what their limitations and capabilities are. You actually calibrate each instrument as well as, or at least document the variability of it against standard reference signals. So, anyway, I'm trying to do that. Some of these are really messy. Magnetometers float all over the place. They're hard to get tied down. People do it. People do work at it. Pieces. I spent 20 years on the gravimeter arrays, on the seismometer arrays, on these other precipitable water. Well, other than a really atrocious color scheme, pardon me, that looks a little bit too psychedelic for me. Okay, so what is it trying to say? This said precipitable water. Okay, it's in millimeters. All right, so that through the whole column of the atmosphere at each of those locations, that many millimeters precipitable. That's how much is floating in the air and can go down and hit the surface. Now, India has a lot. Okay, California is supposed to be having a drought, right? The whole western United States is supposed to be having a drought. And so this here says we're low, right? We have relatively, for some period, oh brother, for one day, I think it is, 22, 210722, at 00 at that time, is that only hour 0, so it's only for the first hour, so that there's that much floating overhead at that time. I think that's what that means. Okay, so what's going on here? There's a ton of water moving along there. That's the intertropical convergence zone. God, it's hard to. I'd love to stick a longitude line along. Let's see. Is that what I'm saying? Zero latitude, whatever it is. Line. Anyway, so I'd like to. I think that's the equator down there, isn't it? Oh, my brain is fried. Okay, so let's see. And there's a lot of this up here. What I would rather do. Can I zoom? No, I can't. I can't click. I can't zoom. So it's really nice. I mean, it's great context and drama. But if I was trying to do something in here, I'd want to go deeper. Snow water equivalent in inches. Shame on you. Centimeters, people, at least centimeters. I don't mind, tenths or hundredths of a meter. I mean, a millimeters even. Just put it in scientific notation. There. So there's that. Snow, accumulated snow. It's middle of the summer in the United States. 1 hour total precipitation in inches. Again with the inches. Though that's really hard to see. I can barely. I can't. Let's see if I can open this in a new tab. Oh, brother. Okay, so now I have to zoom this out. So it doesn't zoom itself. You didn't provide an image viewer. You could take a standard image viewer for all of NOAA, for all of the gov domain. Have about 5 people, super smart people out there, do their best to ask people to contribute them, or share globally. Who's got the best image viewer in the entire universe, where we don't, when you throw something and want to look at it more closely like this, you always use the same thing. Not every programmer on every website in every department writing their own component there. Shame on Google Chrome. They should provide those tools, all of the thing, instead of just taking the junk that people send to you to the browser. You should say, give me the content, and I will put it in a standard display, and in the whole world we'll all work together to get the best visualizations, the best thing. I love contours. But these are not labeled. These are not color coded. there's no 3D view of it. Okay, intrinsically, what is this? It's a three-dimensional view of something. So in that dimension of whatever's being, what is this thing anyway? Precipitation that's there. All right, so if I save the image again, oh, well, PNG is not too bad. Let's do that. Let's look at it again. And this, oh, there it is. Pardon me, properties, details. So it's different than the other one, 692 by 696. The other one was 700 something. I think it was 712, 696, something on that order. So you can't even stack these if they're not that simply. Okay, let's get back down to the size. There's got to be a better way to do this, folks. Okay, 1 hour total precipitation. There's a lot of interest in precipitation, but you notice there's no economic impact on this map. Okay, where are the farms? Where are the people? How much money are they paying for their water? Should they be paying more for their water over here? Okay, there's all kinds of issues and all that. This is a very one-dimensional thing, and yet intrinsically, it's there. How many? If I looked on the internet, which I do every day, I could actually go find every map of the United States in a graphic on the internet, and then look at all the different layers of things that people have put on there, and then think about it, and all the things they haven't put, which is what are the cities and people impacted, where they're. All of a sudden, I'm thinking about India. India gets a big dump of water at one time. California, let me put it in U.S. terms. California gets huge dumps of water. A bunch of it runs off and doesn't soak in. It evaporates out faster now that the land is warming more. And so people are, I think, I don't know, it's hard to get it. It takes me a week to figure something like that. Okay, I'd have to work my usual, 12 to 20 hours a day for a week just to go get what I would feel would be a reasonable picture of what's going on in the western United States. My impression is that, yes, there is a drought. Well, now, the historic low for Lake Mead is only 5 years old. Okay, I'm pretty sure I'm correct on that. It goes up and down all the time. I don't know of any. I haven't found a record. I hadn't had time to look. What's the variability in Lake Mead? Does it go up and down hundreds of feet, every 5 years? If that is, then new news about big swings in the surface and the depth of the water that's not big news. So anyway, all right, so more water, temperature, centigrade and hectopascal. Why did they do that? Shaded and hatched. Oh, okay, so there's hatched. So you did pressure. I can't. Oh man, this is a pain. Open this in a new tab. Not that one here. Go here. Let's zoom this. So they're dotted here. That's not a hatch. Maybe that is a hatch. Okay, so. All right, there's one legend for color. What am I looking at? Oh, everything got blown up. Oh, that's this one. Sorry. No label on this. Temperature, shaded, hatched. What the heck is going on here? Is this ought to be labeled temperature, okay? And if the, let's see, where does this go from? It goes from in here. We don't have anything. I would rescale that. I wouldn't use this, the same one here. Yes, I know in the winter it goes down there, but this is summertime. Use the summertime scale. Actually, just do a min-max and gridded off nicely. You can use the sides. Okay, let's go back to full size here. So that's the picture. This there. Where's the thing? Sorry. Okay. There. Oh, that's there. Here we go. All right. So look at all the space over here you're not using. You got this. If it's a desktop, it's almost always wider than it is tall. Okay. So this here could easily be laid out here. You don't. One of the things you put it below is then this thing gets really long. Look how much we're using. Maybe a third of the, or less than half of the screen, and come on, in there. Okay, look at all the variability in the color schemes. Okay, let's go back to here. Where was I? Okay, so we're wow, those are really striking, aren't they? Okay, so I still don't get that one. Once the magic word, some bit of explanation. I should be able to go here. There ought to be an information button on every one of these. And I'm talking about a hover button like on the Wikipedia's is not good. It's nowhere near what's possible, but it's better than nothing at all. So you could hover this and immediately know who created this, when did they create it, what software did they use, what data did they use, how can I get the same stuff? What else is available that might be here? This all could be done on one thing with layers. There are tons of tools out there on the internet that will layer these things here. You're forcing a change of color scheme. I'm having to adapt to a completely different visualization strategy in most of these, and so I guess what I'm saying is I don't know who's doing these things or who's designing them, but they're not, in my opinion, they're not working together. Okay, they're not working as a coherent team. Now, if this is just a few people and contractors in the United States, then where's the international community that you could be serving, that you ought to be working with and collaborating? This should be a global collaboration. Who in the world? Okay, how many countries? A couple hundred countries? Most of them at the level of sophistication to at least use, and many of them did better what's being done here if they just had the tools and the data. So the people who have the data ought to make it easy for everybody to use. The people who write the software should write it so that everybody can use it. Not proprietary dependencies, not locked, methods, not hidden methods, not obscure methods. So anyway, for some reason I like this, but I don't like it. The relative humidity again. Now, this is 850. Oh boy, millibars. Hectopascals, I kind of, I've done, and I still don't like that hatching. I don't know what they're doing. In why, you have pascals everywhere. You have pressure everywhere. You have relative humidity everywhere. Just make it 2 layers and give me a slider, and I'll change the transparency, right? Okay, set the intensity of each one. If you actually did that mathematically, you could scale the coloring to match. It could be monochrome. You could use red and blue. Okay, the amount of red being the amount of relative humidity, and the amount of blue being the amount of pressure. Let's see, relative humidity can I scale those on the same units? Just a moment. So relative humidity depends on the temperature and the pressure and the wind speed, the height, the density as the composition particularly. I'm going through the entire atmosphere all the way out as far as I can, trying to look at every possible city. we're looking from space here, presumably looking down through the atmosphere. Is there anything that we can do? This is a prediction, or is it? This is a forecast. These I still don't. I don't. I don't know who did this. I don't know when it is. It's hard to tell. This is the valid time. I can't loop through an animation from here. There's a bunch of things. So now the staff and resources at NOAA, there's a finite number of people. But if you look at that, what is going on here? I think there are roughly 25,000 universities and colleges in the world. There are about 1.92 billion kids from 5 to 20, and then another few hundred million or so they're going to there. And then there's almost 2 billion lifelong learners, okay, who at various times have to retread, relearn, learn ahead of time to anticipate changes in jobs in a global society now, where everybody is going to be changing jobs every 5 minutes. When we grew up, our parents worked at one job, or that was the thought at one time. People worked, 20 years, 50 years at one thing. But now, 20 days is a good deal. 20-minute gig might be what you can do. So I'd love all these visualizations, but I'd like to say, well, look, show me all of these with this visualization. Okay, I like this visualization. I like this color scheme. Now, there are good, nice, wonderful ways to fit and slice color schemes. Okay, and you're not using any of them. Okay, you're using human eyeballs, human guesses, human artistic sense to color these things. They're not related to the real things. Temperature, you can put it in KT terms. You can do it in electron volts. You can do it in joules per kilogram. You can do it in joules per cubic meter, which would be an energy density. The energy density can be related to the wind speed. You can tie things together and slice and dice the dimensions of these things. They're a lot. All right. Look at that overlaying there. So somebody's kind of there. Boy, is that pastel and hard to read. It's that thing there. You put your softest, weakest ones in here. You put these strong colors over here that are not good, and you didn't use enough colors to do it. Now, I know that what you can do is go in and interpolate. And what the heck is this? This is vertical velocity. Okay, it doesn't change much, but pascals per second times 10. So this is in 10 pascals per second. Pressure, vertical. What did they do? Geopotential. I can't tell what they're doing. Okay, you may have to show me the equations and the calibrations. That's busy looking. Now, if you had like infinite zoom on this might make sense. I wrote one, but let me use a standard one. Let's see. Okay. Oh boy. Okay. I really got it blown up here. Okay, so I can look at this, but your pixels are so large. There, you could use a finer scale on your map, and then you could zoom down further. Okay, so you say, well, we can only put so many pixels on the screen. I say, well, tile it and go down as deep as you want. So you can't. Now, why would you do that? Okay, why would you do that? Well, we're out here at a goes east kind of a view, geostationary satellite view of the thing. Well, we ought to be able to go in and zoom down and look at my neighborhood. Now, there are tools for doing that out there. And if you get these things compatible with what everybody else is doing, then you're part of a global community. You swap and mix and match and try different algorithms, display algorithms, data communication algorithms, statistical algorithms, physics, and chemistry algorithms. I mean, all of those things can be shared. I've tried to find all of them. I've been at this 23 years now on the internet, pretty much every day, and pretty much 12 to 18 hours a day. So vorticity, 10 to the minus fifth per second. I would use different units. Vorticity is the rotational energy. I've gone through this, I've studied vorticity, its uses, where people talk about it, where people use it as a concept, where they try to model it, where they measure it. 3D vorticity maps. Somebody does a 3D volume scan of something, you can calculate the vorticity at any point. If you know the velocity at every point, you can calculate the vorticity at every point. But often, with things like magnetic fields or gravitational fields, if you look at induced vorticity, or it's on a microscale where much of the stuff that goes on is independent, and so you can actually have the spectrum of the vorticity. I'm trying to get that straightened out. So at the tiniest scale is the gravitational field. That's the most fine-grained field that we've got. It's a physical field because it's affecting, everything. It acts like an electromagnetic field of a fine grain with a low traveling wave velocity. Okay, it's a standing wave. Okay, fine grain, fine spatial grain, standing wave. That's my best representation for it now. So this thing here, if this were a gravitational field, it can just move and slowly. If you remember the old quantum wave functions for an object, you got a rock, you can write its wave function. What it is you start with, let me look at the acoustic, the audio, vibrational spectrum. Let's look at the rotational energy spectrum. Let's look at the ionization, electron spectrum. Basically, you cut through all the energies on the 3D volume in there. And you can, what is it? It's a representation, it's a standing wave, okay? And in 3 dimensions, and the Fourier transform of that is both the stationary spatial representation of the thing, and it's a traveling wave. So I'm trying to get I'm just winging it here, remembering all the little pieces. When I go work on that problem, I throw everything else out of my head and I fill it up and do it right. But here I'm just talking about stuff. So anyway, absolute vorticity. A lot more we could do with vorticity. There's tons of instruments that can measure vorticity. We're just not doing it. And vorticity is tied to the Reynolds number and the fluctuation spectrum and the small scale properties of the thing, which gets down to, anyways, there's a lot of rich stuff there. And when you go to do absorption spectrums for sound and electromagnetism and for gravity, you have to get down to that level. Sorry. I'm just throwing in stuff that I think about every day. I'm trying to put all the pieces together. I'm trying to get it so that the whole internet works efficiently. It's about 1,000 times slower than it ought to be, because you get a group over here, you get 10,000 groups all doing their geopotential maps, and they're not working together. Let me check, I'll tell you. Geopotential height. Okay. 693,000, okay? So if you chop it, generally these are really small groups because that's an eclectic thing, and not many people in their life go out and produce a lot. Many of these are duplicates, so they'll be there. Let's say there's 10,000 groups out there. Okay. Now, why would I say group? Because it might be a few people occasionally, but they're usually in a place like an organization or an environment where they're encouraged to talk about those things. It's a standing issue. It's a standing thing that they work on. and all. So Wikipedia doesn't, let's see, where's one? I just wanted to show you there. So that's a hover box. That's a hover box. These are the most primitive hover boxes you can get. This entire thing is hand built or drawn from a specific place that has to be maintained in the other page. It's a preview of the page on conservative force here, and it doesn't allow you to just see the. In my world, if I could make my own browser or ask somebody to make one for me, I would say, give me a preview hover of everything so that I could go here if I wanted to say highlight that, right, and hover it. I could go and look at that. I could highlight and hover it. I could highlight that, hover it, and have it do. And then you wouldn't have to go do it. If you saw a term you didn't know, here they're basically saying, well, look at me, look at me, look at this, go look at that. Well, that's a judgment call, and I don't know that I trust single individuals, however individually qualified, to be telling me what to go look at from this page. Okay, but if 100 million people came to this page and all went and looked at primitive equations on their own, undirected, then I would say, hey, that's probably at least a popular one, if not fundamental. You know what I'm saying? So a lot of the verbiage in here is not the correct way of saying things. Okay, here's one. And I don't, North Mesoscale Model, NOAA, National Weather Service, it came from there. Actually, it doesn't say weather.gov, so this is kind of mushy. Okay, let's see. Okay, so they're NCEP, NOAA.gov. Okay, so they're, the best geopotential data in the world is from Grace follow-on. I'm pretty sure that there, and that's housed on a different part of the internet in Europe. It's there. So okay, all right. Sorry, this is. Let's get back to where it was. Way back here. All right. That's rather garish. You can rescale these. I mean, no. Okay, if you're training people to be like monkeys and memorize the colors, so that I've got 5,000. Well, actually, probably don't have more than 500 people. 500, 5,000, 50,000 people. I don't know how many people come in there and stare at these things. Do they use it? How much could they use it? They can't gain a visual memory of this because you're going to change these colors on them. Okay, so you could. It's best to just use the numbers. Okay, just share the numbers and let people do their own visualizations. And say, look, let me open this data behind this image in my own visualizer, and I'll look at it. Okay. I might just go and take it into the. Now, I just was looking at this thing here. Okay. This is you guys, our Center for Environmental Information. And first, let's see. Pueblo, Colorado. I pulled in a day's worth of radar data. Level 3 radar, next gen level 3 radar, and man, there's a bunch of stuff. 17,909. I think it is. Maybe it does. It didn't say. They don't give me a number. Okay. Anyway, this seems. I can't change the projection. I can't tell it not to bring up a picture. Okay, so there's limits there. The text on here is right at the limit of what, okay, I can barely read that at all. I get an eye strain immediately. I do it, but I have no way to change the font. Okay, so this is, whoever wrote this they probably are well intentioned and they're very skilled, because there's lots of good stuff in here. When I go through, the access and the connectedness of this are outstanding, but the problem is I can't use it very well because I can't see. Okay, I'm getting old, my eyes are tired, and the a lot of this stuff. If I change the font so I can see yours, I can't see anything else because it won't work. Okay? I found a balance point for Windows. I'm in Windows, and I can't change this. What I think is needed is just, instead of using hard-coded C forms, like if you're using Visual Studio or something like that, or hard-coded whatever language. I don't even know. You don't have an about on here that I can see easily. Is this an open data project? Is this an open software development project? Where, where's this thing? Could I go and change it to fit? Some of it might be practical. I just want to change the font so I can read it. I want to change the thing. I lost. Where's my local disk? I went to look at the other tabs and it threw away what I was doing. And 17,000 files is not shabby to have to go grab here. So, all right, so bring them back. So these in NetCDF, I can export these to NetCDF. I can go to MATLAB and bring them up as objects and read the properties. I can't read the properties of this file there, even though this translates to NetCDF, and I can go there. It requires me to download it, to go into MATLAB, write a little program. I have to write some statements, and so you could expose the properties and history, the provenance of this data in here if you would do it. I can't. Let's see. Oh, missed it. Let's see. You should have maximize, minimize, and mid. Okay, these things. You should have these things here. That means to go full screen. Now, why? Because I might just. I've actually brought this in and only use this tab here. Okay, this window. I don't even look at that because I don't want to look at it. To me, this is fundamental, and that's a visualization. You get what I'm saying? I would bring this up first and then go to that. Now, everybody's got different things. If you like looking at pictures all day, fine. It stimulates the brain cells, it's entertaining, but you can't communicate it. What goes in your head, you can't just give to somebody else unless you give them the data, the visualization tool, and make it easy enough and standard enough in terms of usage globally. I'm talking about for all 7.8 billion people on the planet, to make it universally accessible and easy to use. The difference is about a trillionfold. Okay, if you cut out the massive duplication on the internet, the lack of standards for presentation, there are no two pages on the internet that are the same. Even within any organization, every department does their own thing. Every individual does their own thing. Every group working on weather data does it differently. I went through the nuclear data people. I went to the plasma people. I've gone through the gravitational people. I've gone through close to 20,000 slices of the internet over 23 years. In detail, spending days digging and figuring out, like here, you spend a week looking at the National Radar System, look at the associated data sets, look at the people doing it, look at their plans and standards and goals and organizations and funding, all that stuff. And the basics is everybody's doing their own thing. And why am I making this long video? It's kind of just rambling around on this topic, is to say things like that. We need to fix it. Okay, now not by chopping and throwing things away. Somebody will say, "Well, let's just make it all this way." Well, no. The human species survival depends on variety. Okay, I have a long life of looking at that. I think that um, the reason we the there are so many things happening on the internet. It's almost like a huge boiling pot of evolutionary ideas coming together, and independent development, and everybody starting and looking at it from different points of view is healthy, strong. It's survival positive. Okay, but when a thing has matured, and that's basically like that one. What did I do a little bit ago? It was, how many was it? It was 693,000. Okay, that is a mature topic. Okay, I I worked on I've worked on the geopotential for a 3-letter government agency when I was just about 20 years old. Okay, so it was my first full-time job. And so I know about that. I worked for NASA on the geopotentials. Okay, so it's one of my favorite topics. I studied it in great depth for 40 years. I've loved it. That they, but there's not that many people doing it. Now, when you go and put these in here, actually, it was here. Where were we? When you go using, when people realize that all this is joules per kilogram, that's all the doggone potential is. What they say? Gravity in a gravitational acceleration is just an acceleration. Okay, so it's the same thing. A potential is just a potential. When you get down to that level, then you can spend your time not working about changing. Well, I got to use these units over here, and I got to refer to Bose and Einstein over here, or I got to refer to Boltzmann here, or to somebody. I got to remember all these names. You can get down to remembering the units that are used and say there. Then worry about, well, how accurate is it? How do I measure it? How do I calibrate it? How do I do correlations? How do I do time of flight correlation? So if I've got a gravitational sensor sitting down in here, actually if I have a gravitational array over this whole area, how do I get it how do I know that it's measuring the atmosphere correctly? Well, I'm going to do one thing. I keep repeating this thing. I don't know how many times. All right, let me see if I can remember where I put it. So this was a rather obscure place. I'm sorry. Hackaday.io. Let me close that off. Comes up. There's my projects. This one. Okay. I keep saying that. Come on, open up. It's slow. More than about 20 years ago, I looked at the gravimeter arrays. Okay. And I found the superconducting gravimeters, and I wanted to measure the speed of light, the speed of gravity. Okay, you can't, but they floated all over. Every individual station didn't have a baseline, and they changed all the time. And the reason is they were using a model of the tides in the Earth, when what they should have done is use the direct gravitational vector tidal signal at that location and then subtract it. That's what I did here. I used the JPL positions for the center of the Earth, the center of the Sun, the center of the Moon, the GM for the Sun and Moon and Earth, and the station position. That's it. Then what did I do? I calculated GMM over R squared, the gravitational acceleration, Newtonian gravitational acceleration, at the station, okay, and then subtracted off the gravitational acceleration, like of the Sun at the station minus the Sun at the center of the Earth, the Moon at the station minus the Moon at the center of the Earth, add the centrifugal acceleration term for the station on a rotating Earth, and then dot that or rotate that into station northeast and vertical. So this is the vertical portion of that signal, just the one axis of the tidal signal. The other ones look the same, by the way. I'm trying to get a nice visualization to show. Here's this goes up somewhere around 800 nanometers per second squared down to minus 1,000, minus 1,500. Okay, so that's the variability. It's a huge signal. This residual in here is the atmosphere. Okay, that's done about most of that. Yes, it's going to have some seismic in it. It's going to have some magnetic in it. It's going to have human stuff. By doing this, what does it take to do this? To fit this requires one offset number and one multiplier. This is a month-long thing. Now, yes, there's some quibbles, and you might want to do it daily, or you might even want to do it hourly. I did all of those. But for a lot of stuff, you can say, look, I'm going to work on a weekly basis, or I'll do an annual thing. It doesn't matter as long as it's agreed on. You can have every one and make it a different product. But here's an offset and a multiplier. That multiplier, if you look at it, it's like 1.19 for this one, which is close to that Lamb number that they get. So it's in there. The problem is the support network for the Earth tide models is soft. The groups kind of work together. They don't all do it all the time. It's not a continuum. But anybody can go run GMM over R squared from the JPL horizon system, or run the solar system ephemeris from JPL and get this precisely. It's in Python. I wrote it in Pascal. I wrote it in JavaScript. Okay, so you can. It's just the Chebyshev polynomials. You take their data, you run the numbers. It's a couple of hundred lines of code. Okay, so but the offset on here, I wish I could bring it up. I can't. I'm tired. The offset in here is a exact record of what's going on at the station. These are superconducting gravimeters, helium cooled, and when the helium level changes, the baseline changes. So all of these things you couldn't use the data moment by moment because they were going up or down. So this one is the offset's 152. So this one had to be corrected 152 nanometers per second squared. Okay, it says downward, so it was floating high by 152 there. Now the G factor in there, how did they get the G factor, which is a local calibration? So they run a drop. Let's drop the rock, or drop the molecule, or drop something and measure it. Instrument, very costly, very time consuming, and never permanent. Okay, so you don't have to do that. You can just do this exact same regression. It's a linear regression. That's all it took, one linear regression, an offset and a multiplier. That's the entirety of all of the apparatus that's needed. Is it hard to get that's assuming the position of the sun, the position of the moon, the position of the station, that you get what I'm saying, position of the Earth. So you need some basic data, but if you trust JPL, which I do, they've got a good data set, and then you just do this and then worry about it. And then you publish a standard residual from your station, or you let people have the raw data. It doesn't matter. Say if they have a better way to do it. There are a bunch of things. The Sun Moon Barycenter does matter, and on some places it matters quite a bit. I don't know if it's a secondary effect. There's all kinds of stuff I don't know. I'm just one person who went through all the superconducting gravimeter stations and did this for all the years that I had at that time. And I found all the broadband seismometers that have the same thing, but they have all three axes. And I begged and pleaded and cajoled and tried to get people to build 3-axis, time of flight gravimeters so you can build arrays. That's what I'm trying to build, imaging arrays so we can see the interior of the Earth. We can track. If you blow this up, I mean, it's just a matter of scaling now. Take off the signal, the raw, what I call sun moon vector tidal gravity signal, that big swinging thing there, and take just the residual. Then you're working on atmosphere. That's all atmosphere, and that has enough information in it if you within an array with time of flight methods to image every part of every voxel in the atmosphere. It actually also can image any voxel inside the ocean or inside the Earth. It can do a network of these can also look inside the moon. They can look inside the sun. It's just a pointing or array pointing. If you do a global network, which is all I'm trying to do, where every country has low-cost methods so they can share this sort of stuff, they can be involved. It's not one giant gorilla, 800-pound gorilla somewhere in the world eating up all the resources. Everybody can try it. Every one of the, billions of students, well, they're not billions of students. Do you count a student only when they're in there in the first time learning phase? They go through for the first time, or when they're in their 30s and they've realized all the things they've missed, and then they go back and study even more, or as they mature and need something, they go find it. The people who start new industries and companies, the experimenters, the world is rich in this. I can go every day and see the people working on the internet who are struggling to work together and don't have the tool. So anyway, that's my pitch for gravimeter calibration, 3-axis. Why is 3-axis important? Well, if you do, I measured this, basically I could say that the speed of gravity had to be identical to the speed of light. Okay, that was easy. And to within a second out of 499 seconds to the sun. You can go a little further than that if you could use the whole of all of the superconducting gravimeters, but there is no standard or verification on their pointing, their vertical orientation. Okay, I begged the people who made that thing to let me help them calibrate the vertical thing. You can measure it. The information is there, and if you calibrate it against the sun-moon signal, then you have an absolute standard. Okay, this is absolute. The sun and moon GMs don't change that much. Okay, I think the sun does. I'm pretty sure that if I go dig deep enough, I hope I can find variability eventually. I might have to go down to the femto level or smaller, but if you dig, there are people working on every facet of everything. So anyway, so that to me, that's just so elegant, and so and it gets all of the sun moon stuff completely out of the picture. Why does it work? At 1 sample per second that this stuff is running, the speed of light, the speed of gravity is so fast that the whole system comes to equilibrium quickly. 1 second is almost out to the moon. So there's plenty of time for things to come to equilibrium. Now, if you up the sample rate, you then basically have to do the full geometry and do it there. And then that's when following out what happens when you raise the sampling rate, which got me to understand that you can. Sorry, I was going to talk about how do you use arrays of these and calibrate them. Well, you're going to get magnetic signals that are being picked up by this, because you can't distinguish a magnetic gradient from a gravitational potential gradient. They're the same thing for all practical purposes at these frequencies. And many of the infrasound and then other types of signals, electromagnetic signals slowly varying, all kinds of stuff is going on in there. And the only way to sort it out is to do everything at time of flight sampling rates, or at precise times and exposures and signal gathering times, so that coordinated to the nanosecond or femtosecond or whatever you can get, and then you can determine where's the signal coming from. So you do time of arrival at the array and figure out where does it come from. Now, all right, I'll do one last pitch. I've been begging and pleading and telling people for years now. I said, please go look at this, because this signal is so stable, so huge at the, for these kinds of things, that you can, okay, there were seismometers in the transportable array in the US. They are broadband, and you can see the sun-moon signal on every axis. The horizontal axes are noisier, quite a bit noisier, and it has to do with the fluctuation, the noise, the electromagnetic noise, the gravitational noise in the horizontal and vertical directions. That's a separate issue. But the residuals, when you do a linear regression over a long period of time, okay, so this is 86,400 samples a day times 30 days, however many that works out to, and just at the nominal thing, and what does it do is the residuals go up like crazy if you shift this by a tenth of a second. Okay, the sun moon stuff, you can calculate it at whatever fine scale you want. If you want to calculate the gravity at a place every hundredth of a nanosecond, you just plug in the numbers and do it. It takes more time, but it doesn't change. Okay, that standard of calculation, that source of reference material from the JPL, from that whole network of people, is available at that fine a grain. Now, so anyway, what happens is you can change the orientation. What does this all depend on? It depends on the orientation of the axes of the instrument. If you change the orientation, the signal changes. Okay, so you can. I call it gravitational GPS. Okay, it's more like a gravitational compass, because you basically, if you point it there, you can solve at any time for what direction is this thing looking at. Now, it turns out I'm getting down there. I've been 3 years now, almost full time, at least every day or every week, somewhat fairly steady, trying to sort out exactly what is the fine-grained spatial scale of the gravitational field, and how is that mixed in with the fine-scale magnetic potential. Okay, so I use energy density a lot, because if you're in a vacuum, it's kind of hard to determine. So I use energy density when I'm working in the vacuum, and I use potential, joules per kilogram, when I have a material there, and it's just a density. Now, anyway, so the MEMS gravimeters, which are modified cell phone accelerometers, sensitive enough to measure this signal, there are a bunch of them now. Okay, different groups in the world have done that. Everybody says, oh, we ought to be able to do this. They go and do it, and then they stop. And I've been begging them, trying to say, go calibrate the doggone thing, minute by minute if you want to, against the sun and moon signal. You know the absolute reference. You know the baseline for this. Look at the swings. Okay, so maybe, this is only once a day, but you can calibrate it every day. And actually, these lines in here, the absolute levels, the travel, the trajectory of this is precise. If you're doing it that time, and this is what the signal looks like at the station. This is what it's doing. It's not going randomly all over the place. Can you see? Okay, You can see just a little bit. I can't even zoom in on this really well. Maybe I can. Let's see. How can I do that? I hate you can't do anything on these things. Okay, all right. Everybody does it different. Okay, so that's why I would like when I get an image like this on the internet, I want to put it in my own viewer. Then I have one way to deal with an image. I always know that I can set the fonts for it. I can make it as large. I can zoom infinitely if I want to. I can export the data. You know, we ought to do that. We shouldn't rely on browser companies that don't know anything about science and technology to be giving us tools. Okay, yeah, they have more money than God. They should be able to do it, but they don't. They don't focus on what people need. They just sorry, I'm getting tired and I get cranky. So, all right. Well, that's the pitch. That's what the signal looks like at a seismometer station. Is it messy? Is it a horrible gobbledygook in some ways? I got seismic events here. I got these spikes. It doesn't follow exactly the. What you need to do is you take the Fourier transform, find the clean times, get the Fourier transform of the signal, divide it by the Fourier transform of the sun-moon signal. Okay, and then you have a generalized transform that you can use to map one directly into the other. I can do it by counting states and correlations. There's a dozen ways I've come up with to go in and make this. To me, if I get it this close, the rest is just easy peasy. It's just mechanics. Okay, what you've done when you get it in here, you're on an absolute scale. If the signal is going like all over the place, I can show you so many variations. I mean, these signals will shift massively, right? Because the baseline shifts. Well, that the pieces in here have to match the sun-moon signal. This is over a month, right? So now it could this be done better? Yeah. One person part-time for almost 20 years I've been doing this, been trying to get other people to look at it, to calibrate all the seismometers, upgrade them all so they work as gravimeters. That is, they work at least a 10th nanometer per second squared each second for a one sample per second thing. What that means is you can push the sensitivity up higher and run these things as high as you want to. I've looked at that. I know how to balance. You push the gain, you can go really far. Why? Because when you're down in there and you're looking at the small variations, you're looking at minute by minute, microsecond by microsecond variations, you can learn. Okay, that's what this. You talk about machine learning. Well, you actually a lot of times it's just statistical counting. It's just saying, what happens in there? Where's my signal? How big is it going to be? What's its max and min? What's its average? What is the histogram of the states that it can be in? And what are the histogram of the states, the transitions? Basically, again, you can do it as Markov process. You can do it as Bayesian sequences. I can give you 50 ways people can do it. You can get it. The main thing is to start and say, look, I've got a gravity signal that is an acceleration. I'm monitoring, the second derivative of the position of anything. It doesn't matter what, an electron, an atom, a small cantilever, in an atomic force device, the vibrations of a surface. We have acceleration is embedded in everything. From F equals ma. It's in every part of our society. And how's it tied to gravity? An acceleration is an acceleration. If you trace it back and say, well, this acceleration is correlated or connected to the sun and the moon, like I'm doing here, then you got that piece done. You got what I'm saying? And you can go study it. You can go say, well, look, I know that there's a mass ejection on the sun. can we get our gravimeter array, our accelerometer array, to look at that more closely and trace it? And you might just put bounds on it and say, look, I'll only accept the signal that comes in at the speed of light. Now, it turns out, my guess is gravity is just the low frequency part, these large scale source electromagnetic energy density, if you like. I'm trying to say it in a way that you can give you an idea. That comes at the speed of light. Okay. I would say that it will refract if you've got the rate of change of clocks varies with the gravitational potential, which means if you flip it around, it means that the index of refraction of the vacuum, you can allow that to change. And then you don't have to change anything else. You don't have to say this is something special going on. I'm doing this really, weird gravity thing. You just say, no, we know that at this height, at this geopotential, that the local clock is going to be off. Let's correct it. Okay. And do it. It's just numbers then. Well, let me stop. I've talked for 90 minutes, and I was tired before I started. Is anything? Oh, this is another one. This is Bandung, Indonesia. And you can see the little bits of blue. The actual signal is the blue. Okay, I took the sun and moon and mapped it onto the station and set the base. Okay, so I would do it the other way. Normally, if I could ever get anybody to help me and do this routinely, I would turn it around and I would calibrate the station against the sun and moon signal, that the sun and moon signal would be the standard. These are to the proper scale, so they do mix, but the level of it I would set maybe at 0. You get what I'm saying? I guess that's the part of this that I would change. Now there's these, I don't know if you can read that, it says 1.18, so that's the Lamb number for there. It fits there. It makes it easy to go in there. Look at the residual. Okay, there's the atmospheric variation. Okay. There's probably some earth tide. Some actual like resonances and timings and tides and all kinds of stuff. Rain coming in and changing things, but it's down at that level. If you take this sun-moon signal out, you can get down there and actually use this. Okay. Right now they just do ballpark corrections because we fit the curve. Well, I said no. That's a trivial part of it. Get that done, calibrate it, and then use the residual. Okay. Use the Earth-based data signals that you can do. All right. Well, let me stop here. Are there any more? Let's see. That was that one. That was that one. I don't know what the other ones are. Thanks for listening. I don't get me wrong. I love what's going on here. I love the potential of it. What I don't like is everybody doing their own thing and not working with. Now, it's one thing. Individual creativity and excellence is wonderful, but survival of the human species and the whole world depends on everyone working together. Not one country trying to stomp over other countries, not one city or one university trying to go grab stuff. Everybody fighting for prominence and fame and whatever. Now, as a practical matter, if you get this in the right form, any kid in the world who's learning and wants a job out there can find things that they work with well, and they could just come in and learn and run and improve your models. If you give them tools so they can write scripts to change things, they'll go in there and start trying new visualizations and doing things. If I had tools like this when I was a teenager, when I started thinking about these kinds of things, I would have already been doing that. But I've had to use this clumsy programming languages all these years. So I had to wait basically 60 years almost to get the tools to do some of the things I wanted to do. And almost 20 years now trying to get the crazy gravity data there. The superconducting gravimeters are fine. Bose-Einstein gravimeters would work. Uh, Electrochemical gravimeters would work. Let's see, what are all the ones? Oh, atom interferometer, electron interferometer, atomic force. There's tons of atomic force methods that would work. I could use fission reactions, the neutrons things, atomic clocks. Every quantum nano process in the world is, you can, if you go and look at it, it's going to have gravitational changes in there, from the direct gravitational potential change on the clocks to the gravity tidal effects that change the levels of a lot of things. So if you have a changing voltage anywhere, a lot of that KT noise, some of that KT noise is magnetic, some of it is gravitational. And I think that we're going to find that basically they're the same thing, and it just depends on the spatial scale of the fine grain fluctuations in the field. You know, so, I think of it as a fluid. I think of it as a gravitational fluid, a vacuum fluid, if you like. And the energy is really small. So these are down at the 10 millionth, 1/10 millionth of an electron. Basically, they're at a KT level. A lot of this stuff is at the KT level, and that's for practical reasons. Is because people don't correct for that well. So it's in all the instruments. Everybody stops there. So you could go deeper. So anyway, so our energy resolution could go way down. We could get to nano electron volts, pico electron volts, femto electron volts. If our memories, if our computer memories and our camera sensors worked off of nano electron volt methods, we would be way, way beyond where we are now. Was it possible last year or the year before? No. The reason that we can do that now is because everybody's been pushing down into the nano range, and we have toolkits down there that allow us to go further. And basically, if you go look, you're going to find everybody saying, well, shoot, I don't need to, an electron's way too big for this. I need to look at, tinier parts of that. Look at the magnetic flux quantum. It says 10 to the minus 15th for 1 hertz, 10 to the minus 15th electron volts per hertz. So, and you can go down to nanohertz. So it gets really, really tiny. I'm sorry. I've just so many things I'd like to tell people. There's so many questions I have, and so many things I'd like to do. I'd like to get these things going. This would be great if this. I don't know if this is a projection. I can't tell. There's so much. Okay, how many? NOAA three. How many is in? I don't. Site. Oh, I missed it. Sorry. Yes. I mean, 1.92 million. Okay, that's too many to be curated. Too many to be everybody doing their own thing. Too many cooks. Too many different ways of doing things. You can get a collaborative system where all the people on inside and working on the site, using the site, all work together. That's the dream I've had for almost 23 years now, that all the people using the internet can all work together. So everybody doing fisheries, okay? So how many fisheries are there? And I can't even write it in all the language. I can't even do that many searches. Okay, fisheries, 75 million. A mature industry, mature global topic group, a mature global collaborative group that ought to everybody doing their own website, everybody creating their own databases, everybody create. I know there's a lot of sharing, but when you get down to what are all the things you need to be able to use it, people are not sharing that. They don't even seem to know that you have to provide the algorithms in a standard form. You have to make sure all the units are in this, all fit together. It needs a global set of interchangeable parts at a very, very fine scale. Okay, a gravitational array can scan the interior of the ocean and image it. It can scan magma. It can scan the core of the earth. It can scan inside the sun. It can scan inside the moon. It could scan all the planets. It could scan under the surface on whatever moon that was that has a global ocean under the ice. I can't remember the name. Sorry. All right, let me stop here. Thanks for listening.